So the regime was that rho u naught r by mu, which is the Reynolds number based on capital R, much less than 1. So this is a very usual way of reporting Reynolds number, because you should know that u naught and r, these are velocity and length scales. Okay, in a flow there can be multiple or different length scales, velocity scales. Usually velocity scales are more clear, which one you have to take. Length scales can be very different and the results can be very different based on that. So the standard notation is to put a subscript of the length scale with respect to which your Reynolds number is. So for example, you could also calculate an RED, which is rho u naught 2r, which is diameter. Okay, you may see this also reported at some in some textbooks, and people saying, okay, this is much less than 1. Both are fine. Okay, Reynolds number based on a length scale of the sphere is small. Okay, so when you do this, you get the Stokes governing equation. So mu del square u equals grad p, and we know that this translates to E2 of psi equals 0. Okay, so using the definition of E2 for spherical coordinates, we had obtained the we had obtained the solution for psi in this case. So the boundary conditions were that u r, which is 1 by r square sine theta del psi over del theta equals 0 at small r equals capital R, u theta equals minus 1 by r sine theta del psi over del r was 0 at small r equals capital R, and then we were imposing the boundary conditions at infinity, that for r tends to infinity, the velocity basically tends to u naught cos theta e hat r minus u naught sine theta e hat theta, from which we had said, okay, my stream function r comma theta should be something g of r sine square theta, where this g of r for r tends to infinity was u naught r square by 2. Okay, this is what we had done in our last lecture, and from here we had found this g of r by substituting this. So in a way, this is a guess for separation of variables for these spherical coordinates. Okay, so if you guys have looked at the practice sheet, then I'm asking you to do something like this for cylindrical coordinates, which are slightly easier. So you can do a separation of variables, and you can do what we have covered called the eigenfunction expansion for this equation. Okay, you can do that eigenfunction expansion for this equation. Even for spherical coordinates, that is possible. When I upload the notes, you will see that. Okay, so we have gr. So from by substituting in the governing equation, we had found the solution, and the solution of psi was u naught r square capital R by 4r minus 3r by 4 capital R plus r square by 2 capital R square sine square theta. Okay, this is what we had found for psi of r comma theta. And after this, we were trying to calculate the pressure. So we are interested in the force on the sphere. So for that, we have to calculate pressure and viscous stresses. Okay, we have to calculate pressure and viscous stresses. For pressure, we were saying, okay, we will use this equation. Okay, we can obviously, it is perfectly valid to calculate the Laplacian of velocity using this psi of r and calculate pressure. But what we had said is, okay, I am going to write this as minus mu del cross omega, because del cross omega is going to give me del of del dot u minus del square u, and del dot u is 0 for incompressible flow. So we are looking at incompressible Stokes flow. Okay, every time throughout this course until unless specified, we are looking at incompressible flows. So we have grad p equals this. So we had computed the vorticity we had also computed the vorticity, and that came out to be minus 3 u naught capital R by 2 r square sine theta e hat phi. Okay, this is what we had for vorticity. So then we were yeah. Did we not find vorticity? Velocity, vorticity? Okay. So we can find this. So the way you can find this is by taking the cross product. Okay. So omega, if you remember, is del cross u, and in spherical coordinates this will be given by 1 by r del r. So I have given you del cross a relation, right? You can substitute that here, and this will be del u r over del theta e hat phi. So we know that velocity has only r and theta components. Okay, velocity, which is defined by this in terms of psi. So 1 by r sine theta del psi over del theta, okay, which is equal to, you can differentiate your stream function and calculate the radial velocity. So if we differentiate the stream function in with respect to theta, so we'll just get a 2 sine theta cos theta, and sine theta will cancel out. There is an r square which will also cancel out. So the velocity will simply be, so there will be a cos theta, u naught cos theta, and then I can take this capital R square inside and a small r square inside. Then there will be a 2 multiplying, so you will get 1 plus r cube over 4 r cube, rather 2 r cube, right, and a minus 3 r over 2 small r. Okay, this is what you'll get for u r, and u theta will be minus 1 by r sine theta del psi over del r. So 1 sine theta cancels out, I have to differentiate, and then so this will be minus u naught sine theta. I'm just giving you the result now. 1 minus r cube over 4 r cube, small r cube, minus 3 r by 4 r. So you can substitute these guys here and then evaluate this vorticity. Okay. So put the u r here, put your u theta here, get the vorticity, and this is what you'll get for vorticity. And then what we can do is we can compute the del cross of omega. Okay, we can compute the del cross of omega, and to do that, what I'm going to write it as is, this is 1 by r sine theta del by del theta of this quantity. So I'm going to write it as omega scalar e hat phi. Okay, so this will be 1 by r sine theta del of omega, or maybe just write it as del omega by del theta. So this is what the e hat r component is, and then we have minus 1 by r del by del r of r times omega e hat theta. So this is what you will get for del cross omega. And so what we can write it as is, so grad p, so this is a vector. Okay, this is also a vector, right hand side is a vector. So what we will get is del p by del r equals minus mu by r sine theta del omega by del theta. Okay, we are trying to integrate for pressure using this equation. This is a vector equation, so we will get two derivatives, del p by del r, 1 by r del p by del theta. Okay, we'll get the partial derivatives using which we have to compute the pressure. So this is what you will get for del p by del r, and if we differentiate our omega with respect to theta, so we will simply get, so this is our omega, So we will simply get minus 3 u naught by 2 r square cos theta, right. So minus mu by r sin theta. Hold on, just a second. I think I made a mistake in the formula. So these formulas will anyways will be given to you, so you don't have to remember them at all. Okay, if these formulas are required, then they will be given to you. So this is sin theta. So the correct expression is this. Okay, is there a question? So minus mu by r sin theta del by del theta of minus 3 u naught capital R by 2 r square sin square theta. What will we get when we differentiate this? So we'll get a 2 sin theta cos theta, sin theta cancels out. So del p by del r will be what? 3 u naught capital R by, so mu by r cube, right, by r cube times, so sin theta cos theta, sin theta cancels out, cos theta. Okay, this is what we get for del p by del r. Let's calculate del p by del theta. So grad p, the theta component of grad p is 1 by r del p by del theta. That will be minus mu times the theta component of this guy. Okay, so which is minus 1 by del r r omega. So there will be a minus 1 by r del r r omega. So this is mu by r del r of minus 3 u naught capital R by 2 r sin theta. What do we get from here? We'll simply get a 3 u naught r mu over r cube sin theta. Okay. So there is a 1 by r minus 1 by r, so 1 by r square, and then you'll get r cube in the denominator. Yeah. Del by del theta minus 3 u naught r by 2 r square sin square theta. Yeah. So this is the definition, no? So there's omega times sin theta. Omega already has a sin theta, so that's why sin square. That's exactly the mistake also I made. So this has to be E hat R, just to complete this. And so this is what we get for 1 by R del P by del theta. Okay. And now we can evaluate what our pressure is. Okay. We can evaluate our pressure is, we have to give that at infinity the pressure is P infinity. So far away, for R tends to 0, for us, for R tends to infinity, pressure is P infinity. Okay. And so I can use, there's a minus I am missing. Oh, no, it's all fine. So I can basically use del P by del R equals 3 u naught R mu by R cube cos theta. So I can integrate this and I can say that, okay, integrate it from R tends to infinity to some radius small r. So this will be simply P of R minus P of R tends to infinity equals 3 u naught R mu cos theta dr over R cube infinity to R. Okay, and from here we will get that P of R minus P infinity. So you know that if I am integrating it with R, there has to be an arbitrary constant f of theta that I have to add. Okay, I have to add an arbitrary constant f of theta. So P arbitrary constant with respect to R f of theta, and this f of theta can be evaluated by using del p by del theta. Okay. It just turns out that in this relation you can probably already see that f of theta will be a constant. So, we can just absorb it in p infinity and forget about it, which is again the reminder of the fact that absolute value of pressure has absolutely no relation to the flow. It does not matter to us. Absolute value of pressure does not affect the flow at all. Okay. So, we will get this is what 3 u naught mu r cos theta. So, what will we get here? Minus 1 by 2 r square, right, and then from infinity to r. So, at infinity this is 0, only the upper limit will survive, plus f of theta. So, this is basically 3 minus 3 mu r u naught cos theta over 2 r square plus of f theta plus f of theta p r minus p infinity. You can write. And so, from here we know that del p by del theta, when we differentiate this expression in theta, we will simply get. So, compare del p over del theta with this guy. This guy satisfies this. Okay. This term already satisfies this relation. So, basically we will get that f prime theta is 0. So, f theta is some constant. Yeah. You can't see the part. How about now? Okay. So, when you compare del p by del theta from here, you will simply get f prime theta equals 0. So, f theta is just a constant and we do not care about it. So, we can happily put it to 0. You do not have to always, I mean, you have to be very careful in putting these arbitrary constants to 0, and the idea is you have to relate when is this constant not going to affect the flow. Okay. If there is a quantity whose derivative only appears in all the governing equations and everywhere, then that quantity's absolute value does not matter, because Navier-Stokes equation, in the incompressible Navier-Stokes equation, the absolute pressure does not appear anywhere. It is just grad p. Okay. So, I could have pressure as some constant plus some variation, and that constant will vanish when I take the gradient. So, that is why we say that absolute value of pressure in incompressible flows is meaningless. Okay. It is just the variation that counts, and variation is captured by that. So, we write that P of pressure is simply P infinity minus 3 mu u naught r over r cube cos theta. Okay. Oh no, 2 r square. And so, pressure on the sphere is what? P infinity minus 3 mu u naught over 2 capital R cos theta. So, this is very important, because if you remember our picture of the sphere, so this is just a ring that I am making to highlight that this is a sphere. Okay. So, this angle is theta. So, this angle is theta. So, what we are going to say is that look at pressure variation. What is cos theta in this region? In this region on the downstream side, what is cos theta? Positive. Cos theta is positive. So, pressure is less than P infinity. Okay. Pressure being less than P infinity. Pressure by definition is positive when it is. So, if you remember, the force is given by minus grad P ds integration over the surface. That is how we define the force due to pressure. So, this is the pressure force. How do I know this? Because the total force I had defined is basically del dot T dV. Okay, actually not grad PDS, PNDS. My bad. So this is basically T dot NDS. That is what the force is. Now T dot NDS, T had a minus P times identity plus the velocity gradient terms. So if I'm just looking at the pressure component, pressure part of that, this is what the force due to pressure is given by. Okay, so if pressure is basically force is opposite to the direction of n hat, and that if pressure is negative, then force is in the direction of n hat. Okay, so if your pressure here, this is less than P infinity, so you will see the variation of pressure compared to infinity something like this. Okay, so here I am plotting P minus P infinity. Okay, P minus P infinity, which is negative. P minus P infinity, which is negative, and I am denoting what is the local direction of force or local force that is exerted on the sphere due to pressure. This is not, of course, this is, I mean, pressure is not a vector, so these are not pressure lines. This is essentially locally the force that is being acted on the sphere due to pressure. And similarly, here you notice that pressure cos theta is negative because this is after theta pi by 2. So pressure is higher than P infinity. So essentially P minus P infinity is positive. Positive of gauge pressure or positive of differential pressure will exert this kind of a force. So this is how the pressure force will look like. So you see that there will be a net force in the x direction due to pressure. This is just an intuitive feeling of this. We will derive this x direction force, and I mean we will derive from the relation that it is only in the x direction. Okay, and to do that we will use this. So I'm not sure if you guys are comfortable with this. Are you guys, do you guys understand how did I write the expression for force due to pressure? If anyone has a doubt, please say, because this is, I mean, this is the bare minimum take home that I expect you guys to take after this course. How to write pressure given these flow fields and anything. Even if you don't know how to solve for the flow fields, pressure and everything, if someone gives you those, at least understand how to calculate the practical quantities that are required after that. In most of fluid mechanics, we are always interested in what is the force due to this flow on an object. Okay, so if someone gives you the flow, let us say, you should at least know how to compute the force due to that flow quantity. Yeah.
So what is the magnitude of P infinity here? Because I was a little confused about when you're taking negative on the right side, and
Hmm?
so expression of PR theta equals P infinity minus
Yeah. Yeah.
and so you're saying that the magnitude of P infinity is uh, lesser than 3 mu here.
No, no, no. I'm not saying anything like that. I'm saying P minus P infinity, which is minus through
Okay.
mu u naught cos theta over 2r. This is less than 0 here. This is greater than 0 here. Okay. So the pressure force is simply minus P n ds over the spherical surface. Okay. I can also write this as, instead of P n ds, I can write it as P minus P infinity n ds. Why? Because this is basically, I mean, P infinity n ds is 0. Why is that? So why is this quantity 0? Why is this quantity 0? Why is integral of n ds 0? Sure, intuitively, okay, you are making sense, but how do I derive? How do I show this is 0? Huh? How do we show this is 0?
Every n cap has a diametrically opposite.
Again, intuitively, you guys are all right. Okay. I do not doubt JEE cleared candidates in on visualization, but how do I show this? Are there tools that we have learnt in this course from which you can show that this is 0? This is 0 because this is what? 1 into n hat ds. If you apply Gauss divergence theorem, this is del of 1 dv, gradient of 1 into dv, which is what? 0. Okay. So this guy is 0. So that's why I can write this as this. And p minus p infinity is something that we know. So the equation becomes, the force due to pressure becomes 3 mu u naught over 2 r cos theta n hat ds. Okay. What is n hat? What is n hat for? How can we write n hat for a spherical surface? What is n hat for a spherical surface? What is the unit normal for a spherical surface? Cos theta I cap plus, so let's say this is I cap, this is your x, this is y, and then this is z. So what are the other guys? Huh? Sin theta j cap. ऑलरेडी आई और जे में तुमने एन हैट का मैग्नीट्यूड 1 कर दिया, अब कुछ भी ऐड करोगे तो एन हैट तो यूनिट नॉर्मल ही नहीं रहा. So what is the remaining thing? So you have to understand that this n hat could be anywhere here. So there are two angles, don't forget. So remember this ring on the spherical surface. So there is, as your friend said, over this whole ring, the I cap component is cos theta. Okay. So I cap component is cos theta. But what about the j cap and k cap? I mean, even if you think that why are j cap and k cap different, think about it. If on the ring you are here, then k cap component of n hat is 0. If you are here, then j cap component of n hat is 0. There must be something that is changing over the ring, which is changing the components of n hat on j cap and k cap. So if you have, let's say you are somewhere in between, so on the ring you have an angle phi that we always trace in the spherical coordinates. So cos theta is in I cap. Yeah. So first we have to, so there is cos theta in I cap, then we take a sin theta in the j cap or k cap plane. Okay, and then sin theta times, so depends on how you take the angle. Let us say if I am viewing from this side and this is your ring, let me rub this. Let's say this is your ring and coming out is the x direction, and then we have y and z. Okay, then let's say we take the angle from y as phi. So sin theta cos phi j cap plus sin theta sin phi k cap. That's how we define the normal of the sphere, right? And then ds is simply r d theta into r sin theta d phi. The radius of this ring is not r. The ring has a different radius based on what theta is. The ring's radius is r sin theta. Okay. This is not a, I mean, my drawing is quite bad, but the ring will change its size as you change theta. So ds is simply r square sin theta d phi. What are the limits on theta and phi? So if I substitute these guys here, what are the limits on theta and phi? So the very nice way to avoid confusion on which one has the limits is to write the integral like this. So instead of writing the differentials at the end, you should write the differentials right after their corresponding integral sign, and then things never get confusing. So you have 3 mu u naught over 2r cos theta, and then we have an r square, or rather this r will be capital R, right, because we are on the spherical surface, so r is constant. So we have r square sin theta d theta d phi, or d theta d phi I have already written, and I have to write n hat also. So we will have a cos theta I cap plus sin theta cos phi j cap plus sin theta sin phi k cap. What are the limits of phi? Phi is the angle over the whole ring. So this is 0 to 2 pi. And what are the limits of theta? So theta equals 0 is this side, theta equals pi is this side. Okay, and if you look at the expression inside, nothing is varying with phi except for these guys or these guys. Okay, if you look at the j cap and k cap component, j cap is basically, j cap component will have a cos phi d phi integrated from 0 to 2 pi, and k cap component will have a sin phi d phi integrated from 0 to 2 pi. What are these integrals? Sin phi d phi 0 to 2 pi, what is it? 0. Cos phi d phi integrated from 0 to 2 pi is also 0. So the j cap and k cap components are basically vanishing. Okay, and all you will be left with is, and the rest of the terms of I cap are not varying with phi. So phi will just integrate out. So you will have a 2 pi times 3 mu u naught by 2. So this into r, and then an integration of sin theta cos square theta d theta from 0 to pi. Okay. So what are these? What is this integral? Sin theta cos square theta d theta. What is this integral equal to? Hmm? With the limits, tell me. So there will be a minus cos cube by 3. Minus cos cube by 3 will be there from 0 to pi. Minus. So what do we get? Hmm? 2 by 3, right? This will be minus of minus 1, minus of minus 1 again. So there is a 2 pi 3 mu u naught r by 2, 2 by 3, which gives us 2 mu u naught r. So the and of course I cap. So the pressure force is there in I cap direction, and it is equal to this. Yeah, there's a pi also. You're right. Okay, so there is a pressure force component to the total force, and now we will try to calculate what is the viscous stresses, viscous force on this. Okay, and to compute the viscous force, what we have to calculate is, so if you recall, your T, the stress tensor, was this guy. Okay, minus P delta Ij plus 2 mu Sij. So what we essentially need to calculate is the viscous stresses. Okay, so I, J, K are 1, 2, 3 or R theta phi. So this I am going to write as small tau Ij, and I need tau R R, tau R theta, tau theta theta. Okay, and basically this is a 3-dimensional problem. So there are tau r phi, tau theta phi, tau phi phi, and all of those as well. But we know that flow is axisymmetric. So there is no variation of the flow in phi direction. Okay, and if you look at the definitions of these stress tensors in, if you look at the definition of these stress tensors in the spherical coordinates, you will see that those guys are 0. So these kind of things will be given to you. I mean, the definition, what is the del in spherical coordinates, what is the curl in spherical coordinates, and all those things whichever one is required in exams, that will be given to you. But you should understand that why only 3 of these components are expected to be non-zero. We'll just show that actually only one of them is non-zero, but you should understand why only 3 of them are expected to be non-zero. So the definition of tau theta theta is actually 2 mu 1 by r del u theta over del theta plus u r over r. We need to calculate them on the sphere. Okay, we need to calculate them on the sphere. So just by looking at the expression of tau theta theta, can we argue that this guy is 0? Just by looking at the expression and knowing that we need on the sphere, we need this guy on the sphere, can we argue that this is 0? So we are on the sphere, we know that velocity u r is 0 on the sphere. And the other thing is u theta, which is the tangential velocity, that is 0 everywhere. That is 0 for all theta. U theta is 0 for all theta. Why? No slip. So del u theta by del theta is 0 due to no slip. It's like saying if you have a flat plate and you have some flow happening here, let us say there is a flow happening here, but you have a flat plate and u equals to 0 at some y equals y naught for all x. So that means you can say that del u by del x is also 0 at y equals y naught. Basically u is 0 for all x here. So the x derivative, x partial derivative is 0. So theta partial derivative is 0. So tau theta theta is actually 0. What about tau r r? Let us look at tau r r. The definition is 2 mu del u r over del r. So we have computed the u r velocity, right? We have computed this radial velocity. U r is basically given by u naught cos theta 1 plus capital R cube by 2 r cube minus 3 r over 2 small r. I need del u r over del r at r equals capital R. What is it going to be? So it's going to be u naught cos theta. What do we get from here? Minus 3 r cube by 2 r to the power 4. And what do we get here? Plus 3 r over 2 r to the power 2. At small r equals capital R, what is this? At small r equals capital R, what is this? 0. So del u r by del r is also 0 and tau r r is 0. So that means we are going to be left with just tau r theta. Hopefully tau r theta doesn't turn out to be 0. We'll just see. So the definition of tau r theta is mu r del by del r of u theta over r plus 1 by r del u r over del theta. Okay. And there's no, by the way, I mean, if some of you are concerned about, okay, this is just formula plugging and everything that's happening. So remember that most of the maths that was going to happen has already happened. We are sort of understanding what are the practical quantities of interest after we have calculated the flow field. Okay. And in that, it's all basically plugging in the flow fields back into the equations and trying to find forces and stuff like that. Okay. So that is essentially what is going on. Now some of you might be like, okay, how do I know that these are the definitions? There's no shame in looking at textbooks for these definitions. Okay. And actually it comes through practice that you will know it off the top of your head after some time. Even I, at this point of time in my career, I don't know them off the top of my head. Okay. And At least I'm not ashamed of that. Okay. So in my opinion, there's no shame in accepting that you don't, there's no way you can memorize them. The best way is to use them often and to develop an intuition, and then they'll be off the top of your head. Okay. So these things are mostly you will find in all uh, fluid mechanics textbooks in the appendices. There'll be an appendix dedicated to cylindrical and spherical coordinates always. Okay. There's a way to derive these, of course, if you look at generalized curvilinear coordinates. So if you go through the additional or optional section of chapter 1, I have given you all the tools to understand how to derive these. Okay. But you don't need to know that at this stage. So this tau r theta, if we compute, so we have u r, okay, and we have u theta also. So u theta was minus u naught sine theta 1 minus capital R cube by 4 r cube minus 3 capital R by 4 small r. Okay. So substitute this u theta and that u r, and you will get that tau r theta is, so I am just writing the final relation here, minus 3 mu u naught over 2 r sine theta. Remember, all of this has to be evaluated at small r equals capital R. Okay, substitute this u theta, substitute u r from there, and you will find this is the relation. Now you can make a similar intuition about this tau r theta stress. Okay, you can make a similar intuition about tau r theta stress. So tau r theta. So if this is your sphere, let's say, and this is that ring. Okay, tau r theta is basically. So what is the intuition from your first solid mechanics course of tau r theta? What does tau r theta mean? If you were to denote it, what does it mean? Sure, it is a shear, but there is more you can say about tau r theta, right? What direction it is occurring in and things like that. So tau r theta can be understood as either of the two. One way is it is the force on a surface normal to r direction and the force is in theta direction. Or you can flip this also, that it is the force on the theta on the face normal to theta direction in the r direction. Okay. Remember, tau ij, writing it as tau ij or tau ji, even before we proved it was symmetric, we showed that it is just a matter of convention. Okay. So usually some people get very sentimental about, oh no, first index is normal, second index is direction. Some people get sentimental, no, first index is direction, second is normal. Doesn't matter. Okay, it's all convention. And as long as you're looking at very plain continuum mechanics, solids or fluids, we know that tau ij is going to be symmetric. So it even doesn't matter after that. Okay. So here we expect that tau r theta, so the normal of the sphere, normal of the spherical surface is the r normal, right? So it is the force in the theta direction. So it is like this. Okay, this is your theta. So tau r theta can be, of course it's not a force, it's a scalar. Okay, you have to multiply it with n hat and do all the integration, which we will do, but just to give an intuition of what is the force on a small elemental surface on the sphere, it's the tangential force. And now you know sine theta for 0 to pi is what? Sine theta 0 to pi is positive. So tau r theta is negative. This is the direction of theta. So you understand that this is tau r theta. So over the whole sphere, tau r theta is basically the shear force on the spherical surface. Okay, it is like this. So as the flow goes past the sphere, it is trying to stretch this skin of the sphere. Okay, and usually this is why the drag force due to viscous stresses is often called the skin friction drag. It is like it is acting on the surface and it is trying to stretch the skin of the surface. Okay, and you can obviously intuitively imagine why this is called a friction drag. Okay, this is a friction, this is due to viscous stresses on the surface. So this was the intuition, just like pressure that I gave, but we can derive the relation also here. So we'll write Fv, that is the viscous force, and I want to write that what is the force due to viscous stresses. So force due to viscous stresses will be, so this we wrote as tau. So the force is tau dot n ds. Okay, tau dot n ds. Okay, and tau r theta, you can write tau r theta as this. Let me call this as tau. Okay, or even if I don't call it as tau. So this is the tensor. Tau r theta is simply e hat theta e hat r. Okay, and then the n hat is also e hat r. So this is simply ds, and we get that this is tau r theta e hat theta ds. So this manipulation is very important. Okay, this manipulation is very important. Please understand this. Go back to our tensor discussion. Understand why I wrote it like this. Remember what second order tensors were. There was a tensor basis e hat I, e hat j. Okay, there is a tensor product which I have basically omitted. Okay, there is a tensor product that should have been here. I have omitted that. So it's e hat theta e hat r dot e hat r. E hat r dot e hat r is 1. So we get a e hat theta ds now. So
At R also.
huh?
This could also have been instead of E theta cap, could have been E R cap also, because you said that I mean tau r theta can be taken in either of the directions.
Yeah, yeah. So there'll be two components here, and then check what tau r theta e hat r ds. Actually, if this is tau dot n, technically there are 9 components in this stress tensor. Okay, if I have tau r theta and I know that stress tensor is symmetric, then I know that there is a tau theta r as well. I know that there is a tau theta r as well. Okay, so technically this tau dot n. So that's a good point. That's a good point to make, that Fv is tau dot n ds. This is technically going to be equal to tau r theta e hat r e theta dot e hat r ds plus tau or theta r theta e hat r dot e hat r ds. What is this? What is e hat theta dot e hat r? Okay, this guy is 0, no? So the only thing that remains is this. N hat is always E hat R. N hat is always E hat R by definition. So the flip component or the symmetrically opposite component, diagonally opposite components contribution is actually 0. And from here, so remember that this N hat was, the N hat that we wrote was E hat R. This is how we denoted E hat R. So in the same spirit, how will we denote E hat theta? In the same spirit, how will we denote E hat theta now? So this is E hat theta. How do I denote it in terms of I cap, j cap, k cap?
Minus cos theta.
Minus cos theta I cap minus sin theta I cap, and then same thing, no, plus cos theta cos phi j cap. Okay. After you convert, so this is E hat theta, this is E hat theta sin theta, and then E hat theta cos theta is in the yz plane now. In the yz plane, same things are happening. The angle of phi is with respect to j cap, so this is cos phi j cap plus cos theta sin phi k cap, and ds remains as it is. This ds. So again there is an integration over phi, and these guys will cancel out because this is sin phi d phi 0 to 2 pi, cos phi d phi 0 to 2 pi. So j cap and k cap components cancel out, and what you will be left with is, so this is your tau r, so you will be left with 0 to pi, and there will be a 2 pi 3 mu u naught r from this r square, and then a sine square theta, and then a minus of sine theta d theta. Okay, this is what you will have. Okay, this sine theta, there's a minus here, there's a minus here, so things cancelled out. So, and you have a sine theta from here, you have a sine theta from here, you have a sine theta from here. So essentially we have to integrate sine cube theta. Okay, what is the integration of sine cube theta from 0 to pi? What is it going to be? Hmm? What is the integration going to be from 0 to pi sine cube theta? So this is 6 pi mu u naught r 0 to pi sine cube theta, which you can write as sine theta 1 minus cos square theta d theta. Okay. So this is simply 6 pi mu u naught r. What is sine theta d theta 0 to pi? What is sine theta d theta 0 to pi? Oh, there is a 2 also here, right? I forgot the 2. So this should be 3. Sorry about that. Please fix. So the r cancelled with this r square and gave us r in denominator, and there is a denominator 2. So this is 3 pi mu u naught r. What is sine theta d theta 0 to pi? Half or 2? 2. And then we have a minus of sine theta cos square d theta. What is that? We just calculated sine theta cos square d theta. What is it? Minus of 2 by 3, no? So this is sine theta cos square theta d theta 0 to pi, which is exactly what we did for this place. So this is essentially 6 pi mu u naught r, if you take this inside, minus 2 pi mu u naught r, all times I cap. So this is your viscous force, and then when we say that the total force, which is viscous force plus pressure force, this guy will cancel out, and you will get the drag, which is the relation that you guys know as well, 6 pi mu u naught r. Okay. So go through all of this derivation, go through this derivation in the textbook. I'll upload the notes at some point. You can look at that as well. And this is how we derive the total drag force on the sphere.